This is Physics 2211 Lab 3 going over black holes. Now, in part A of the experiment, we have a star orbiting a black hole of an unknown mass, and we need to estimate the mass of the black hole by analyzing the star's motion. Now, we know here that the net force on the star is caused solely by the black hole at the origin, so we know that net force equals the gravitational force. Also, what we know is that the black hole here is at the origin, so a zero vector, and then the mass of the star is 2.0 times 10 to the 30th kilograms, and then the gravitational constant, obviously, is 6.7 times 10 to the negative 11th Newton meters squared per kilogram squared. And we also have a randomly generated set of initial position vectors for the star that we can use to calculate the momentum and velocities. Now, to calculate the net force, we can use the simple net force equation, change in momentum over change in time, and then we can calculate the force parallel for visualization purposes by taking the change in the magnitude of momentum over the change in time multiplied by the unit vector of momentum, and that gives us a parallel component. And because we know that the net force is equal to the sum of the perpendicular and parallel components, we can just subtract the parallel component we found from the total net force and then get the perpendicular component. And then finally calculating the mass, because we know that the net force is just influenced by the gravitational force, we know we can just simply isolate one of the mass variables in our gravitational force equation and then move variables around accordingly and then get the equation seen here on the right to get the mass of the black hole. And then also the net force here needs to be a scalar, so we just take the magnitude of the net force. This is a calculation loop that just applies everything. So it uses velocity components to define initial and final velocities. Then it, gets the initial and final momentum vectors by multiplying by mass of the star. Then then gets the change in velocity and change in momentum. Finds the net force. Then finds the parallel and perpendicular components, and then uses the equation we found here on the right to actually calculate the mass of the black hole, which is found to be 1.09 times 10 to the 34th kilograms. Now this video just shows the visualization of it all, and the different arrows represent the different forces, and you can see that the force, the net force is the orange arrow, the force parallel is magenta, and then the blue one's the force perpendicular. Now part 2, we have a ship landing on a planet orbiting a black hole, and we need to determine what initial velocity the ship needs to leave the planet's surface, pass by the black hole, and not crash, while also not getting into any sort of orbit. And we need to do this by calculating the forces acting on the ship, which would be gravity from the black hole and the planet, and then on the planet, which would be gravity from the ship and the black hole. This calculation loop gets the forces on the planet. It takes the position vector of the black hole to the planet, which would be planet's position minus black hole's position. Then gets the unit vector, r hat, by dividing by magnitude. And then it finally gets the force of the black hole on the planet by plugging all these values into the gravitational force equation. It then does the same for the ship to the planet by just replacing black hole values with ship values. And then you add the force of the black hole on the planet with the force of the ship on the planet to get the net force on the planet. This part gets the forces on the ship, which essentially does the same thing as before, except it does the black hole to the ship first, and then it does the planet to the ship, and then it just adds the two forces gotten together to get the net force on the ship. This part of the calculation loop just updates positions and velocities. So it takes the net force found on the planet and then on the ship, and then applies that to the velocity update formula taken from the momentum principle, and then applies this to the position update formula. And this is a snapshot of the visualization of it all to show that it doesn't get caught into any orbit and doesn't crash into anything. And it was found that a velocity of negative 10 times 10 to the 6 for the x component, and then 9 times 10 to the 6 works in the y component. And this works just to not crash and to not getting caught in any orbit. And then also it goes in the negative direction for the x component because it needs to pass by the black hole. Now, different values do work for the velocity. This was just found to work through plug and chug method, so definitely other stuff is applicable, but this is what I just found to work for me. Now, what does that all mean? How are the net force and its components different from the rate of change in momentum and its own components? Now, mathematically, they're equivalent, but the net force is actually conceptually what causes the change in momentum. And in this scenario, acceleration leads to change in velocity, which leads to a change in momentum. Now, what if we actually did want to orbit the black hole? What initial velocity is needed to enter an orbit around the black hole? Now, I found that an initial velocity of negative 9 times 10 to the 6th for the x component, then 9 times 10 to the 6th for the y component. That works to give it an elliptical orbit, and the same thing applies here. it's in the negative direction for the x component just so it can pass by the black hole still. Thank you.